is meant by partial differentiation. So partial differentiation is the process of finding the partial derivative of a function is called as partial differentiation. In this process, the partial derivative of a function with respect to one variable is found by keeping the other variable constant. So now I am going to tell you about the uses of partial differentiation. Partial differentiation is used to differentiate mathematical formula having more than one variable in them. Partial differentiation is used for finding minima and maxima of optimized problem. And one more uses of partial differentiation is that partial differentiation equations are used to mathematically formulate and thus aid the solution of physical and other problems involving function for several variables such as propagation of heat or sound, fluid flow, elasticity, and electrostatics, dynamics, etc. Thank you.
Topic name is variable to be treated as constants. Let us consider the implicit functions. f1 of u v r theta is equals to 0 and f2 of u v r theta is equals to 0. Example, x is equals to r cos theta and y is equals to r sin theta. Equation first becomes r square is equals to x square plus y square and theta is equals to tan inverse y upon x. And we have to find dab r by dab theta. We need a function which has a relation between r and theta. But in above equations, one more variable x or y is extra. That means there are 4 variables x, y, r, theta. So we have to eliminate only one variable out of 4 variables. From equation 1, we get two possible relations. R is equals to x sec theta, equation second, and r is equals to y cos sec theta, equation third. Now we can find very easily dab r by dab theta either from equation 2 or equation 3, but we get two different values of dab r by dab theta. To avoid this, as to which variable is considered as constant, we use the following methods. W by dab theta means first write u as a function of theta and y and then differentiate u partially with respect to theta, keeping y as constant. W by dab r means first write u as a function of r and x and then differentiate u partially with respect to r, keeping x as constant. Dab x by dab y means first write x as a function of y and r and then differentiate x with respect to y, keeping r as constant.
This is an example of variable to be treated as a constant. The question is if x is equal to r by 2 e raised to theta plus e raised to minus theta, y is equal to r by 2 e raised to theta minus e raised to minus theta, then show that dabba x by dabba r treating theta as constant is equal to dabba r by dabba x treating y as constant. From the question we have e raised to theta plus e raised to minus theta by 2 is equal to hyperbolic cos theta and e raised to theta minus e raised to minus theta by 2 is equal to hyperbolic sin theta. Therefore, the equation will become x is equal to r hyperbolic cos theta and y is equal to r hyperbolic sin theta. Therefore, dabba x by dabba r keeping theta constant is equal to hyperbolic cos theta as the derivative of r is equal to 1. Squaring and subtracting equation 2 minus 1, we get hyperbolic cos square theta minus hyperbolic sin square theta is equal to 1. Therefore, x by r square minus y by r square is equal to 1 from equation 1 and 2. X square minus y square is equal to r square. Therefore, r square is equal to x square minus y square. So differentiating with x partially, we get 2r dabba r by dabba x keeping y constant is equal to 2x. Dabba r by dabba x keeping y constant is equal to x by r. Dabba r by dabba x keeping y constant is equal to r hyperbolic cos theta upon r. R will get cancelled, so dabba r by dabba x keeping y constant is equal to hyperbolic cos theta. From equation 3 and 4, we get dabba x by dabba r keeping theta constant is equal to dabba r by dabba x keeping y constant is equal to hyperbolic cos theta. Hence proved.
Hi everyone, myself Dipanshu Dinesh Raut, roll number 109 from Mechanical B Division. I am currently pursuing my first year BE in Maratha Vidyapasarak College of Engineering, Nasik. So I'm going to explain you about homogeneous function. First, homogeneous function of two variables. A function z of two variables x and y is said to be homogeneous of degree n if it is possible to express z in the form z equals to x raised to n f of y upon x or z equals to y raised to n f of x upon y or f bracket tx comma ty equals to tn f into f bracket x comma y. Now Euler's theorem. First, Euler's theorem on two variables. Euler's theorem on homogeneous function of two variables states that if u is a homogeneous function of two variables x and y of degree n, then first x divided by u upon divided by x plus y divided by u upon divided by y equals to n into u. Second, x square divided by square u upon dabba x square plus 2xy dabba square u upon dabba x into dabba y plus y square dabba square u upon dabba y square equals to n bracket n minus 1 bracket close into u. Second, homogeneous function of three variables. A function u equals to f of x, y, z is said to be homogeneous function of x, y, z of degree n. It is possible to express u as u equals to x raised to n f of y upon x, comma z upon x. Second, deduction form of Euler's theorem. If z is a homogeneous function of x, y of degree n and z equals to f of u, then first x divided by u upon divided by x plus y divided by u upon divided by y equals to n into f of u upon f dash of u. Second, x square divided by square u upon divided by x square plus 2xy dabba square u upon dabba x dabba y plus y square dabba square u upon dabba y square equals to g of u bracket g of u minus 1 bracket close, where g of u equals to n upon f of u upon f dash of f of u.
Example of Euler's theorem. The question is u is equal to x plus y upon root x plus root y. There are two sub-questions we need to find. First, x into dabba u by dabba x plus y into dabba u by dabba y. Second, x square into dabba square u upon dabba x square plus 2xy dabba square u upon dabba x dabba y plus dabba square u upon dabba y square. Here we first find degree. Therefore, u is equal to x into in bracket 1 plus y by x upon root x into in bracket 1 plus root y upon root x. Here we take x common. It is equal to the x raised to 1 by 2. Therefore, the degree is 1 by 2. So, u is the homogeneous function of degree 1 by 2. Here we first find x into dabba u by dabba x plus y into dabba u by dabba y. According to the Euler's theorem statement 1, if z is the homogeneous function in x and y of degree n, then x into dabba z upon dabba x plus y into dabba z upon dabba y is equal to nz. Therefore, 1 upon 2 u is the solution of x into dabba u by dabba x plus y into dabba u by dabba y. Second, x square into dabba u square upon dabba x square plus 2xy dabba a square u upon dabba x dabba y plus dabba square u upon dabba y square. According to Euler's theorem statement 2, if z is a function homogeneous function of in x and y of degree n, then x square dabba square z upon dabba x square plus 2xy dabba square z upon dabba x dabba y plus y into dabba square z upon dabba y square is equal to n into in bracket n minus 1 is equal to z. According to this statement, the solution is 1 by 2 in bracket 1 by 2 minus 1 u. Therefore, minus 1 upon 4 u is the final solution of the question. So, this is an example of Euler's theorem. If u is equal to tan inverse x cube plus y cube upon x plus y, we have to show that x square dabba 2u upon dabba x square plus 2xy dabba 2u upon dabba x dabba y plus y square dabba 2u upon dabba y square is equal to sin 2u into 1 minus 4 sine square u. Let u is equal to tan inverse x cube into 1 plus y cube upon x into 1 plus y by x. We have taken x cube common from the numerator and x common from the denominator. So the equation will become u is equal to tan inverse x square 1 plus y cube upon x cube upon 1 plus y by x. This can also be written as tan u is equal to x square into 1 plus y cube upon 1 plus y by x. Here f of u is equal to tan u. So f of u is a homogeneous function with degree 2. So here n is equal to 2, f of u is equal to tan u, f dash of u is equal to sec square u. For applying the formula of Euler's theorem, we need g of u, f dash of u and g dash of u. So g of u is equal to n into f of u upon f dash of u. Substituting the values of f of u and f dash of u, we get g of u is equal to 2 into tan u upon sec square u is equal to sine 2u. Therefore, g of u is equal to sine 2u. Taking the derivative of g of u, we get g dash of u is equal to 2 cos 2u. Therefore, by Euler's theorem, x square dabba 2u upon dabba x square plus 2xy dabba 2u upon dabba x dabba y plus y square dabba 2u upon dabba y square is equal to g of u into g dash of u minus 1. Substituting the values, we get sine 2u into 2 cos 2u minus 1 is equal to sine 2u into 2, 1 minus 2 sine square u minus 1. Here cos 2u can be written as 1 minus 2 sine square u is equal to sine 2u into 2 minus 4 sine square u minus 1. So the answer is sine 2u into 1 minus 4 sine square u. Hence it is proved.
Hello everyone, myself Pratik Shelar from Mechanical Division B. Here I am presenting a topic of an implicit function. Even when the value of x is known, we cannot directly compute the value of y. Implicit function is a function with multiple variables and one of the variables is a function of the other set of variables. A function f of x and y is equal to 0 such that it is a function of x and y expressed as an equation with the variables on one side and equalized to 0. To differentiate an implicit function, we consider y as a function of x and then we use the chain rule to differentiate any terms considering of y. Now, to differentiate the given function, we differentiate directly with respect to x the entire function. This step basically indicates to use the chain rule. Example, x square minus y square is equal to 9 is an example of implicit function because knowing the value of x do not directly leads us to the value of y. It is also not expressed as y equal to some function of x. Thank you.
Implicit function let f of xy is equal to 0 represents an implicit relation. From this relation, the example, if f of xy is equal to 0 and phi of yz equal to 0, so that dabba f upon dabba y into dabba phi upon dabba z into dz upon dx is equal to dabba phi upon dabba x into dabba phi upon dabba y. The given function is f of xy is equal to 0. To find dy upon dx, using formula dy upon dx is equal to minus dabba f upon dabba x upon dabba f upon dabba y. Second given function is phi of yz equal to 0. To find dz upon dy, the formula is dz upon dy is equal to dabba phi upon dabba y minus dabba phi upon dabba z. Multiplying these equation, we get dabba f upon dabba y into dabba phi upon dabba z into dz upon dx is equal to dabba phi upon dabba x into dabba phi upon dabba y.
Myself Sumit Ranmade from AFE Mechanical B, roll number 107. My topic name is total derivative. If u is a function of x and y, where x is a function of t and y is a function of t, then we can express u as function of t alone by substituting the value of x and y in u is a function of x and y. This du upon dt is called the total differential function of u or the total derivative. The total derivative of u with respect to t is du upon dt. Du upon dt is equal to w upon x into dx upon dt plus w upon y into dy upon dt. This is equation 1. Equation 1 can be written in terms of differential as du is equal to w upon w x into dx plus w upon w y into dy. This du is called total differential.
Myself Vijay Shinde, roll number 113. I am explaining composite function. If u be a function of two independent variables x and y, where x and y are separately function of single independent variable t, then u is called as a composite function of t. If u is a function of x and y, where x is equal to phi 1 t1 t2 and y is equal to phi 2 t1 t2, the u is called a composite function of a two independent variable. Their representation is w by w t is equal to w upon w x into w x upon w t plus w by w y into w y by w t. For a composite function of three independent variables, if u is a function of L m n, the L is equal to phi 1 into x y z, m is equal to phi 2 is into x y z, and n is equal to phi 3 into x y z. Its representation is w by w x is equal to w by w l into w l by w x plus w by w m into w m upon w x plus w n by w x into w by w n. And this application in real life whenever we calculate taxes.
This is an example of composite function. If u is equal to x square plus y square plus z square, x is equal to e raised to t, y is equal to e raised to t sin t, z is equal to e raised to t cos t, find du by dt. Here u is a function of x, y and z, and x, y and z is a function of t. So by formula, du by dt is equal to w by w x into dx by dt plus w by w y into dy by dt plus w by w z into dz by dt. So from equation 1 we have u is equal to x square plus y square plus z square. Therefore, w by w x is equal to 2x, w by w y is equal to 2y, and w by w z is equal to 2z. From equation 2, we have x is equal to e raised to t. Therefore, dx by dt is equal to e raised to t. From equation 3, we have y is equal to e raised to t sin t. Therefore, w y by w t is equal to e raised to t into cos t plus sin t into e raised to t by using u into v rule. Therefore, dy by dt is equal to e raised to t into sin t plus cos t. From equation 4, we have z is equal to e raised to t into cos t. Therefore, dz by dt is equal to e raised to t into minus sin t plus cos t into e raised to t. Again by using u into v rule. Therefore, dz by dt is equal to e raised to t into cos t minus sin t. Substituting all these values in equation 1, we get du by dt is equal to 2x into e raised to t plus 2y into e raised to t cos t plus sin t plus 2z into e raised to t cos t minus sin t. Simplifying this equation, we get du by dt is equal to 2 e raised to 2t into 1 plus sin t cos t plus sin square t plus cos square t minus sin t cos t. From this, sin t and cos t will get cancelled and sin square t plus cos square t is equal to 1. Therefore, du by dt is equal to 2 e raised to 2t into 1 plus 1. Therefore, du by dt is equal to 4 e raised to 2t.